Oh, Zoom. Good evening, everyone. We can get started. We are so excited to have Kate here, who's a professor of computer science and a researcher at Meta. She has done some incredible work in computer vision and multimodal models, and we're so excited to have her talk about unleashing the power of large language models for visual understanding. All right.
Thank you. Hi, everyone. It's great to be back. I was a grad student here many years ago, and I remember moving into this building when it was new, and it had some issues. One of the issues were leaks, and I remember one dramatic moment during my office mate's PhD defense when a leak opened up in the window in the ceiling, and this huge stream of water hit the chair next to his advisor. Thankfully, not the advisor. And to my office mate's credit, he just kept going. He just kept presenting his PhD defense. Just, like, didn't even pause. Handled it really well. Okay, so I'm here to tell you about some recent work that some of my students have done, and these are collaborations that I'm excited about, and yeah, let's get started. So, and by the way, I don't know if you recognize this building. This is our new computing and data science building at BU, and my office is, I think, somewhere here, around here, so I can see you guys from my office. Okay, so the kind of huge, news, of course, in AI these days is large language models, and they're quickly becoming the generic interface for all kinds of tasks. And one of these tasks that they've been adapted to recently is multimodal understanding of, for example, image understanding. So an example of multimodal LLMs or mLLMs is I'll abbreviate. There's kinds of different abbreviations for it: vLLMs, mLLMs. This is one example of a chatbot that can understand images and it can talk to you about images. So someone could ask, what are things I could be cautious about when I visit here? And the chatbot will give you a whole list of things like, be careful about the water safety, weather conditions, and so on. So visual chat, also visual question answering is another task that people have done. Another example is video LLMs. So LLMs that can talk about videos, can understand what's happening in a video, or just describe, answer a question of why it's funny, and answer questions about videos. Yeah, so these are various tasks that people have applied large language models for. And what I want to address in this talk is making LLMs better, or adapting mLLMs to be better at these following two tasks, which is visual classification and understanding long video. Okay, so that's going to be the talk today. In visual classification, these are kind of a special case of visual question answering, because we want to know specifically how an object can be classified. For example, what kind of flowers are these? By the way, does anyone know what kind of flowers these are? It's my favorite flower. Yes, it's a peony. Yes, thank you. Yeah. And so we might want to ask these kinds of questions. And on the right, we have long video understanding, where, as opposed to what I've shown you before, this is the state of the art in video LLMs. They can handle typically pretty short videos. Like you can see, this one is 9 seconds long, so like maybe 10 seconds, 15 seconds. Here, what we want to do is see if LLMs can help us understand much longer videos. And by long videos, I really mean, 2, 3, 4 minutes, maybe up to 10 minutes. Okay, so that is long for us compared to what exists out there. Okay, so the first task I want to talk about is classification, and the paper I want to talk about is called CLAMP. which stands for Contrastive Language Model Prompt Tuning. And this is work done primarily by my PhD student, Piotr, at BU, and it's in collaboration with folks at BU and also folks at UCF and Meta. So back to multimodal LLMs. And so we have this example MLLM called Lava. And it can understand images, and we can ask it questions about images. So if we ask it what is unusual about this image, it can unleash the power, so to speak, of the LLM and say why it's unusual, because it understands not just what's in the image, but also kind of what things are normal and what things are maybe funny or unusual or strange. So that is one of the reasons that large language models are so useful for vision tasks, because they contain this common sense knowledge that previous models that don't use LLMs don't necessarily have. Okay, but what if we ask the same LLM, is this a hatchback? Is the car a hatchback? It says, yes, the car in the image is a hatchback. Well, that's wrong, because it's clearly not a hatchback. It's a sedan. So in fact, when you start asking it these kinds of classification questions, you quickly realize that it's getting a lot of them wrong. And so this is what actually prompted our investigation into this. We wanted to see, first of all, how good existing multimodal large language models are at classification questions, because they're not evaluated on these kinds of questions. They're evaluated on VQA, but kind of VQA has kind of a whole variety of questions. It doesn't focus specifically on classifying objects. So, okay, so you might wonder, why should we use LLMs for classification? Well, first of all, image classification, particularly zero-shot classification, is a very fundamental task in computer vision. So if we want generic fundamental multimodal models that handle many different tasks, I think we do care that they include this task. At the time, or right now still, CLIP is the state-of-the-art model on classification, zero-shot classification. But CLIP can't do generative tasks. So you can't talk to CLIP and ask it questions and have it generate language. You can only kind of ask it, is something in the image or not? So those are some of the reasons. And also, we thought maybe LLMs could help us, in fact, with classification, because they have a lot of knowledge embedded in them that could be useful. For example, LLMs actually know what objects look like. So just text-based LLM, right? So if you just ask that same LLM that I was using, that just the language part of that LLM, not the MLLM, but the language LLM, it can actually describe what a hatchback looks like, how it's different from a sedan. So there's a lot of language knowledge embedded that could be helpful and could potentially improve classification performance. Okay, so some of the examples of these multimodal LLMs that exist right now are models like Lava, Mini-GPT, InstructBlip. Of course, there's also commercial models like GPT-4V and Claude. And at least like the open source models we know about, we know that what they do is they learn a mapping from frozen visual backbone features. So we have a pre-trained vision encoder that we don't change, and then we have a large language model that we also don't change. All we change is we learn this projection layer, the parameters of the projection layer. Okay, so basically they're stitching a pre-trained vision encoder to a pre-trained large language model with captioning loss followed by some instruction tuning, so like a vision question answering and instructions. So the first thing we wanted to do is just to see if we apply these MLLMs to zero-shot classification, how well will they do? And as you already saw, if you just directly ask a question, is this a sedan or something else, they often, like some of them will even have a bias to always say no. So it's not the best way of applying them to zero-shot classification. By the way, the zero-shot just means we don't fine-tune on those specific categories. We just directly test on them. So the way that works the best that current state of the art essentially on applying these models to classification is you feed the image in and then you feed in a prompt that says a photo of A, and then you just generate. So like you generate language conditioned on these two things. And then you look at the first generation and you see and you evaluate, and then you sort of feed in the word minivan, which is one of your classification labels. So you see if the LLM were to generate the word minivan, what's the probability of that word? Then you evaluate this generation probability for all the words or phrases in your label set, and you pick the one with the highest probability. So this is called the GPT score. Okay, so now we have a way of using this model to classify a set of categories. So if you do this, this is what you get. The average zero-shot accuracy across 24 data sets. I'll talk a little more about what the data sets were, but it's just a variety of different kinds of data sets for classification. And you can see that these two multimodal large language models, Lava 1.5 and Mini GPT-4, do much worse on this task than CLIP. Right, so CLIP, as I mentioned, is state of the art for zero-shot classification. So it's getting 48.7 accuracy on average, which is, you know, a huge gap, right? So they're just not as good as CLIP. So that was interesting, and it sort of confirmed some of the things we were seeing, just playing around with these models, seeing kind of how they're not that good at actually categorizing objects into categories. So what can we do to improve it? So like one of the problems is that they don't work well, but another problem actually is that they are not efficient on this task, because in order to do this evaluation, we have to pass the image and the prompt into the model and do multiple passes. So to evaluate, I think on ImageNet, it took just like hours and hours and hours as opposed to minutes for the model that we end up using. So it's very inefficient. It doesn't perform well. So what can we do about it? And the hypothesis we had was that it's not that that LLMs are inherently bad for classification. It's that they're not trained effectively for discriminative tasks. And what I mean by that is they're trained in a generative way. They're trained to predict the next word token. And they're not actually trained to discriminate, you know, like, is this a sedan versus a hatchback, for example. So we wanted to see, with this hypothesis, can we adapt an LLM to classification using a discriminative pre-training objective? Well, I shouldn't say pre-training, training, because if we consider pre-training the LLM itself, pre-training, and also the vision backbone is pre-trained. Now we're training the two to stitch them together. Can we do that more effectively with a contrastive loss? Okay, so that's the idea behind CLAMP, where we, first of all, our goal is to adapt an LLM to zero-shot classification. It's a sort of like almost a proof of concept thing to see how well it would do. If we could do it, and how much better can we close the gap to CLIP, basically. And so in order to do this, we want to align the LLM representation with the pre-trained visual encoder. And to do that, we want to use a contrastive learning objective, which is similar to the CLIP objective. And if you're not familiar with CLIP, it's basically you have image and caption pairs, and you take a positive pair, which means an image with the corresponding caption, and you feed that into the model, and you compute their similarity in the embedding spaces, and you try to make them more similar than a negative pair, which is an image paired with a caption from a different image in that batch, which is assumed to be a non-matching caption. So it's a contrastive objective. So it's different from generative pre-training that like Lava, for example, uses. Okay, so again, to illustrate, so we have the current multimodal LLM training, which is generative. by predicting the next token, versus what we're doing, which is we're going to feed each category into the LLM, and then the LLM will generate an embedding of that category. For example, T1 is the embedding of the first category, minivan, and T2 is the embedding of sports car. And then we also take the image encoder embedding, and then we compute similarity between the image embedding and the word embedding. And then we apply the contrastive training objective. So it's a contrastive training as opposed to generative training. So in order to adapt, as I said before, in MLLMs, they learn a projection layer between the visual features and the language features. Here, we're going to do something similar, but we're actually going to do something extra, which is we're going to do these three things: attention pooling, read-only prompt learning, and LoRa. So all three are ways to fine-tune an LLM in a lightweight way so that you're not updating a lot of parameters. The vast majority of parameters are frozen. But first of all, we're updating attention pooling because we need to combine information across all the words in the input to generate a single embedding for this contrastive loss. And so to do that, we need to train a pooling layer that combines the embeddings of all the output tokens into a single embedding. And then the other thing we do is LoRa, which is low rank updates. So instead of just fully updating the weights, we constrain those updates to be low rank. And we only, I think we only update the attention heads as well. And finally, read-only prompts. This is something that a previous work found successful, where you learn special tokens that are added to your text tokens as input to the LLM. And so what this does is, so if you only learn something at the output layer, you're not changing anything that happens in the actual network, right? So you're not changing the processing that's happening in the LLM because you're stuck at the output layer. So for example, you can tune things a little or pool things, but you can't activate features that wouldn't be activated before. But with prompts, you can actually change the processing in the network itself and potentially like extract new features out of it. But again, in a lightweight way, right? So you're not fully fine-tuning everything. And then to train this model, as I said, we're using a contrastive loss where we're aligning image-text pairs. And we also added a distillation loss, which is distilling knowledge from a stronger clip model. So we have the open clip large 14 teacher model, which gives us predictions for the pairs, and we try to enforce our trained model to mimic that teacher model. What we find is that this actually tends to improve performance because we're distilling from a strong teacher. And so when we train this way, we still hope to retain the generative abilities of our base LLM. So that like after we finish training, we still want it to be able to do chat and generate text and not just do discriminative tasks like Clip does. So we want to be kind of in the best of both worlds. And keep both capabilities. Okay, so let's move on to experiments. So for the base LLM, we're using Vicuna 1.5, which has 13 billion parameters. For the visual encoder, we're using a frozen open clip VITB16. So if that tells you anything. If not, don't worry about it. And then training data is conceptual captions, a subset of Lion, and ImageNet 21K. And by the way, ImageNet 21K is not a captioning data set, but we convert it to captions with kind of template-based conversion. And then for the downstream evaluation of zero-shot classification, we evaluate on these 24 diverse classification data sets that that I'm not listing all of them here, but they include, for example, Stanford Cars and Patch Chameleon, which is like a cancer classification data. So it's a very diverse set of things. There's satellite images in there, driving data, aircraft, and so on. Okay, so without further ado, these are the main results. So I showed you the top 3 bars before. So zero shot clip, which is state of the art, was at 48.7 on average. And with our clamp approach, we are almost reaching that performance. So we're getting 47. So we're able to significantly improve on Lava and Mini GPT-4, which are the state of the art MLLMs, by something like 13%. So this shows that we can indeed adapt a large language model to do well on this task. It's also more efficient. And we also compare it to LIT. So LIT is basically an approach that instead of taking a pre-trained large language model, you initialize the text encoder from scratch and you learn a custom text encoder. So just on the caption data, you're learning a custom text encoder. So you're not transferring any knowledge from a large language model that was trained on like the whole web, for example, or whatever llama was trained on. So we see actually we can even outperform that approach. This is the most, I would say, fair comparison, whereas CLIP is not so fair because it's trained on more data. Yeah, so if we compare it to no pre-training of the LLM, just a custom text encoder, we slightly outperform that approach. So I think this is interesting because it shows us like a proof of concept here that we can indeed adapt a large language model to do well on this task. However, we wanted to dig a little bit deeper and see which data sets in particular the model is kind of helping more on compared to, for example, from scratch encoder training. So we did this analysis where we split our data sets into high versus low coverage. And by coverage, what I mean is how many class labels in the downstream data set are present in the concept dictionary of our training data, so in the image caption pairs and ImageNet and conceptual captions. So that's coverage. So for example, 47% coverage in cars means that 47% of the labels in the cars data set were seen during training. Whereas other data sets like, for example, SVHN and Clever have 0 coverage, means that none of those labels were seen in training. So then on the left, we have all the low coverage data sets, and on the right, we have the high coverage data sets. So high coverage means, like, for example, 100% for something like CFAR, 70% for Eurosat, and so on. So this is just based on text labels. We also include count, which is the average number of pre-training images per class label in the that is in our target data set. And here also you see basically the high coverage data sets tend to have a lot more images as well for those categories. And so what we see is that this LLM initialization helps more on the low coverage data sets where it improves average performance from 29.5 to 33.2 compared to LIT, which is not using an LLM. Whereas on the high coverage, we're basically we're doing worse than LIT by a few points. So we're still outperforming MLLMs like Lava and Mini GPT, but it's just interesting to see that, potentially kind of transferring knowledge from the LLM helps us more in these data sets with labels that we haven't seen in our image caption training data, right? So it kind of makes sense that like the LLM knows something about those labels, and it's improving performance. But the other thing to notice is like actually in a lot of these low coverage data sets, performance is still quite low overall. Like even for CLIP, like this is 0 shot performance, right? So just kind of point out that this is by no means solved problem. Okay, so just to kind of show you that the model, the LLM, still can do generation, we have an example of asking the LLM after we fine-tune it this way. We still ask it questions. We evaluate it on generative text benchmarks, and we see a slight drop in performance, which makes sense because we've kind of damaged some of the LLM by this fine-tuning, but it still does pretty well. It still like is doing better than previous generative LLMs. And so it's nice that we're able to maintain both capabilities of generation and discrimination with the same LLM. And yeah, just to conclude, this paper, I think, shows proof of concept that we could adapt LLMs to zero-shot classification if we use this contrastive loss. I think there could be other ways to do it that are probably even better, but I think this is a first step. But maybe even more interesting to me is just to validate that these models are pretty bad on that task to begin with. And so, yeah, so I think in the future, what I would be interested to see is combining kind of these ideas to have one model that can do both discriminative tasks and generative tasks really well. And so you don't have to like trade off one for the other. Are there any questions that maybe I'll pause for a second here in case people have questions before I move on to the next paper?
Does the calibration play a role here in terms of kind of discriminative models and the kind of generative abilities working as well in discriminative setting?
What do you mean by calibration?
So in the sense that would supervised fine-tuning or other kinds of RLHF style approaches to make the model better at following instructions and or behave as a discriminator better?
Yeah. I think that definitely plays a role because so the MLLMs are fine-tuned on instruction following data, but I think the instruction following data does not include a lot of these discriminative questions. Maybe, I mean, there are some, but I think it still differs quite a lot from like, here's a few categories, can you pick the best one? And they're not very fine-grained questions. They're like maybe, why is this photo funny? Or what can I do with this, whatever it is. Yeah. Yeah, go ahead.
I wonder how did you evaluate the reasonability? Is it from human evaluation?
We evaluated the reasoning ability of the LLM on, I forget the name of the benchmark, but there is a benchmark data set. Yeah. This is text-only reasoning. Okay. So let me then move on to video and specifically long video understanding. So as I said before, for videos, the state of the art in large language models for video is they can handle videos of around 10 to 15 seconds. So in this work, which is led by my PhD student, Ruben, at BU, and collaboration with, again, a few students at BU and folks at Adobe and Meta. So here we wanted to see, well, what can we do about longer videos? And I'm going to show you an example video. So this is a video that's long by LLM standards. And what we ideally want is we want our model to understand what is going on, like what is the overall event that's happening in this video, right? And it's hard because you now kind of like have to sit there even as a human being and watch quite a lot of this video before you can figure it out. And so if you look at this video specifically, it's 9.5 minutes long. And with our model, what we can do is actually support a video of this length and then have a conversation with our video LLM. So we can ask our model to summarize the overarching task the person's trying to achieve in the video in one sentence. And it says the overarching task is to build a raised garden bed, which is basically correct. can you explain why you think the task is to build a raised garden bed and describe which action? So you can actually ask for specific details that happen as well. And it will say, they dug a hole first and they built the frame, then they filled the base of the frame and so on. So it can also give a more detailed description. And we've applied it to question answering as well. So like asking questions about the video and then evaluating like multiple choice style on those benchmarks. So that's kind of the brief summary of the model. And so the key, again, is to extend understanding capabilities from a few seconds to a few minutes to kind of longer videos. So how do we achieve this? So first of all, just to give you a brief overview on video LLMs. So the way they work is we have a short video, let's say 10 seconds, and we want to feed that into the LLM along with an instruction or a question, like describe this video. And the way that they accomplish this is by sampling a few key frames and then tokenizing these keyframes using a keyframes tokenizer. Right, so this gives us keyframe tokens for the video. Right, and for like a 10-second video, maybe you'll have like 5 keyframes, for example, one every a few seconds. Typical frame rate would be 30 frames per second. So you're keeping you're definitely not keeping all the frames. And so if you have a short video and you want to pass it as input to a state-of-the-art video LLM, you would take the video tokenizer, generate the keyframe tokens, then apply a global affine transformation, which maps from vision representation to the language embedding space. And that then gets fed into the LLM along with the text tokens, right? So that's how you would input the video along with the text instruction or question into the video LLM, and then you will generate with the decoder, for example, it would describe the video and you would generate that text. So how can we adapt this approach to a long video? So now we have a long video, so here time goes down and we have, let's say, 180-second long video. So several minutes here, what we could do is still just sample the same number of keyframes that the video LLM was trained on. Let's say 3 keyframes, one at 0 seconds, one midway through, and one at the end, and then feed that into the keyframe tokenizer. But this isn't going to give us good performance because we're going to lose a lot of information. We're dropping like many, many frames now. We're losing a lot of granularity. Okay, so another thing we could do is we could complement this kind of global context. So we can think of these keyframes that are sampled at some fixed number from the whole video. We can think of that as a global context of the video. We can complement that by extracting shorter video segments. And then, so break up the whole video into short segments and then embed each one. And now we can just feed all of them. So each global and all the local segments, we can feed it into our keyframe tokenizer. Now we have just like a whole pile of tokens and we feed that into the LLM. Okay. So we can do that, but the downside here is that passing this extended sequence of visual tokens into the LLM will be pretty inefficient. And so what we wanted to do in this paper is instead adapt this approach, again, in a lightweight way that doesn't fine-tune too many things, but we want to adapt it so that it does more of a summary than just dump everything out of all the frames and shove it into the LLM and, hope it deals with it. Okay, so that's the key idea. So we call this VideoMosaic, and the approach basically is taking the video, splitting it into segments. So here the red is the first segment. Let's say it ends at 15 seconds and we have keyframes extracted there, and then orange is the next segment or a later segment, but we segment the whole video into segments. And then each segment gets passed into what we call a contextualized video segment tokenizer. And I'll show you how that works in a few slides. And this contextualized tokenizer also gets keyframe tokens from the global context. So it knows the local information, also knows the global information. Okay, so this aggregates, each of these aggregates context between frames in one segment and also gets the global context. And then for all the segments, we take the outputs of the contextualized tokenizers, plus again the global keyframe Z key. So Z key is the global, Z segs is all the local segment tokens, and we feed that into another tokenizer that we call the contextualized intersegment tokenizer. You don't have to remember these acronyms. But just the idea is that now we're going to aggregate all the information across all the segments. Okay. So that's the high level idea. And the way we do it is by adapting this pre-trained and mostly frozen keyframe tokenizer function from the video LLM. Remember, the video LLM was pre-trained on lots and lots of videos, but they're all short videos. So it's really good at taking a short segment of video and embedding it into a vision space. So the way we want to adapt it, so this is the keyframe tokenizer, which consists of a frame encoder and a video Qformer. And so we want to adapt this, specifically the video Qformer part. So this is Qformer stands for Query Transformer. So it's a transformer module that stitches vision tokens to language tokens, but by learning queries. So similar to the idea I showed you before with learned queries into the LLM. So we want to adapt this to aggregate context between frames and between segments. So it's kind of it's a hierarchical approach, essentially. Okay, so how do we do this? So here is the video Qformer in the keyframe tokenizer function, right? So this keyframe tokenizer, this is the video Qformer. I'm just zooming in on that part here. So the video Qformer, it has a self-attention layer followed, this is just transformer layers, self-attention followed by cross-attention, which attends from the text to the visual features. And then another layer, so there's multiple transformer layers, and it takes these encoded frame features as input. And so we keep the frame encoder frozen. We don't change that from pre-training. What we change is these learn video queries. Okay, and then it outputs our keyframe tokens. Sorry, we don't change the video queries, sorry, we train the segment queries. So the segment queries are learned prompts, essentially, that we train as additional input into this Qformer. So it kind of it acts as an additional prompt so that it can learn to incorporate the global context that's coming with the keyframe tokens into the local context of that segment of video. So as you can see, the vast majority of everything is still frozen. We're just tuning these or learning these segment queries. Okay, so this gives us segment tokens. For the kind of higher level piece of this, we do the same thing. We take the Qformer as is and just train intersegment queries now, so a different set of learned prompts, and then additional concept queries that are added to all the full segment tokens. And then this gives us the intersegment tokens, so that summarizes over all the segments. So again, most of the parameters here are frozen, just these queries are learned. So it's a low number of parameters that we'll be learning, but it will be quite effective. Okay, and then finally, to put everything together, so we have our keyframe tokens and our intersegment tokens. The keyframe tokens is the global representation. The intersegment tokens is all the contextualized clips that we extracted and their representation. And so finally, for the keyframe, we don't change the global affine transformation layer that happens before feeding it into the LLM, because these are still kind of the same short clips. They're not contextualized, but here we learn a new global affine transformation. So some more parameters are learned here. And then we put everything together into the LLM. Okay, so that's the whole approach. I know that was quite fast, so feel free to stop me and ask me questions if you have any. Yes.
So what pretrained models are you so far?
VideoLLM.
Does that encode the frames as well?
Yeah, so it's trained on short videos, like 10, 20, 10, 20 seconds, 15 seconds. So yeah, that's the keyframe tokenizer that we adapt. That's like frozen, and we just learn the queries that go into it. Yeah. And I'll show you a comparison between that model as is, just kind of applying it to all the segments directly versus what we're doing here. Any other questions? Okay. So to train our model, we train it on the how-to 100 million data set, which is a YouTube data set of lots of videos. There are a lot of like instructional videos, and they come with very noisy labels. Like, for example, it could say, you know, baking a cake, or putting together a chair, a piece of furniture. And so these are these task labels that we train with. And so it's kind of very noisy, I would say, training data. So it's pretty weakly supervised, actually. And then we add this template, instruction templates that we feed into the LLM, like what is the most likely objective in the video, or what is happening in the video. And then the response template will say, like, a person is trying to blank. And then for blank, we insert the label of that task. The person is trying to bake a cake. So that's our training objective. Just, you know, minimizing the negative log likelihood. And to evaluate, we evaluate on a couple of different tasks. So the first one is called ego schema, which is a data set with fairly long videos. It's an ego-centric data set. So you have someone wearing like a headset, and they're recording usually something that they're doing. In this case, they're recording themselves doing something with another person, so you can see the other person, but you also see the camera wearer's hands, like here. And they have questions in this data set that look like this. So what is the overarching behavior of C? C is the camera wearer and the man in the video. And then you're given these options. So it could be C is teaching the man game rules, but the man seems distracted, not paying attention. Or the correct answer here is C and the man are playing a card game while keeping track of it in a notebook. So, like, it's actually hard for me to just look at these few keyframes and know which answer is correct. So it's not an easy task for a computer vision model. But as it turns out, it's easier for a language model, and I'll show you how even just a language model alone is already kind of state of the art on this task, which is funny. So what we do for evaluating is we take 3 minutes long videos and we do 0-shot evaluation. So we don't do any fine tuning or adapting. Okay, so what I mentioned is, what if we just use the LLM itself as a language prior to do this task? Right, so instead of doing this, where we feed both the video and the question to the LLM, we just feed the question and the candidate answers. So the question, candidate answers are what you saw here. So normally we would feed that plus the video, but in this baseline, we remove the video. Okay, and then we choose the candidate answer with the highest log likelihood, given just the question, not the video. And as you can see on this data set, so the random chance performance is 20% accuracy. And for some smaller models, they don't do better than chance, but Llama 2 already is doing better than chance. And then Flanty 5 does much better. So that's one thing that, is always a lesson in benchmark creation, that you should always think of like any kind of baseline you can try, including a blind, like no vision baseline, and see how well it does on your task. So then when we add vision models, you can see a bunch of video LLMs like Violet, Frozen, vLLM, and Video Llama, and then our concatenation baseline, where we take Video Llama and we apply it to each segment and then just pull all of the tokens. And none of them actually outperform just Flanty 5, just the language prior on this data set, which we thought was kind of interesting. But it also shows that the language model here would be powerful, right? Because it's even alone is doing so well. And then our approach is improving on the language prior alone, but actually not by that much, but already is like an achievement that we're doing better, where all the other video LLMs are actually doing worse. Question?
What's your intuition for why a blind language model does so well? That seems very surprising.
Bias in the data set. Yeah. I've seen a lot of vision language benchmarks be proposed over the years, and like there was a visual embodied navigation benchmark where you have a simulator and there's a robot and you tell it go down the stairs, turn right at the kitchen, and so on. And at some point, we evaluated just like a language, no vision. We removed all the vision, and it was beating state of the art. So it's just like there's some bias that basically you don't need vision to solve. And these models are super powerful. So like they just pick up on things in the data set, I think. And by the way, we're not training them on this data set. So it's just like there's something in that data set that it can pick up on. But yeah. Here's another example where the question is, based on the actions in the video, determine the overarching goal of the individual's actions and identify key steps they took to achieve it. First answer is incorrect, which is to create a detailed sketch. The second answer is correct, and that's the answer our model provided. In this case, the individual, I'm cherry picking this because obviously you saw accuracy is not super high even on this data set. But this is one example where it's working well. So it's creating a notebook cover. That's the action here. But also we looked at the kind of attention maps, and we anecdotally think there's more attention on the actual notebook and like the relevant objects here. So we think maybe our model is paying more attention to important things. Here's another example. This is an evaluation on long procedure understanding. This is a different data set. It's also egocentric, I believe, but the task is different. So you're given a long video and you are asked, can you recognize the actions that occur in this video and list them in order? So this is, I think, hard because, you don't have to just understand what the actions were, but you also have to put them in the right order, like close fridge, carry milk, screw open milk cap, pour milk, and screw close milk cap. And I think, again, a language model can help you with this because it knows like you tend to do things in that order. So these are about 4 minutes long videos, and the data set is called Seed Bench. Again, we tried language priors, which are the yellow bars, and then we compared to image LLMs, so just applying like InstructBlip and other image LLMs per frame and pooling. And some of them outperform the language prior here. And then we have video LLMs in red. And so here, Valley and Video Llama 2 are the two models that are evaluated on this data set. And then our approach, VideoMosaic, is actually improving quite a lot on these state-of-the-art video LLMs. But interestingly, even like some image LLMs can do better on this particular task. There's another evaluation on short-term action recognition. So here, the question is just what is the action being carried out? And in this case, the videos are short. So we just want to see after this fine-tuning that we did, can our model still understand short videos? So we do kind of, calibration on that task to make sure we don't lose performance. And indeed, again, language priors, image LLMs, and video LLMs, and our video LLM is the best on this short action recognition task as well. So yeah, that's basically all I wanted to talk about today. We have a demo, by the way, that Ruben set up. So if you're interested, you can check it out. And if you do, you'll see some things I glossed over about, which maybe I'll mention now, which is that these models are still not perfect. They often hallucinate. If you give it a very long video and you ask, like, did something happen? Oftentimes they'll say the right thing, but also insert a bunch of things that didn't actually happen, right? So it's kind of hallucination behavior. But yeah, I think this is like one more example of how large language models can be harnessed for some vision tasks in video with some success. So yeah, that's it. Thanks for listening, and have time for questions. Maybe we can take questions. Yes.
How does the model retain the temporal information, since it seems like the hierarchical approach with some tooling? So how does it know like what action happened?
That is a very good question. I actually don't know the answer to that. I'm going to guess like some position embedding. So like an embedding of where you are in the video, but I'll have to refer you to the paper. Yep.
I was also surprised by the fact that the pure language models were sometimes more effective than some of the video ones. Do you have any sense of, you mentioned to the previous question that it was bias playable. If for some of the models that does do better than random if they were trained on the data set, or if that kind of just the textual part was somewhere the training core
That's a possibility. Yeah. Sometimes there's data pollution. Yeah, I see that sometimes. I don't know about these particular data sets, but yeah, that's a very good question. I know for some of the image captioning and image VQA data sets, sometimes there's data pollution, and you see that like Blip, for example, is trained on Coco, and then it later gets evaluated on Coco, and it's like, oh, it's doing so well. Yeah.
You mentioned hallucination as one kind of ongoing challenge. Are there other sort of consistent failure modes you've seen with this type of approaches? Or is hallucination kind of the biggest issue?
Yeah, I mean, I would say like hallucination, which is just a type of error, like specifically predicting things that are not in the image. But another failure mode is predicting things that are in the image, but getting the detail wrong. Like instead of saying, sedan, saying hatchback, for example. So like it's close, but it's not the right thing. I think in general, they're probably better like at their in-domain training and pre-training data. So that's always going to be true. Like, if you put in like, I don't know, something out of domain, I don't know what it would be, but maybe like a movie or like a sitcom, like, I don't know, because our training data set specifically is YouTube 100 million data set. So whatever is not in YouTube would be out of domain. Yeah.
I'm curious because the taking keyframes approach is kind of to reduce the compute requirements of the method. Is there like, I guess I'm curious if there have been any human studies for like when people can pick up on certain things happening at certain frame rates, like as you, I don't know, is there some kind of guidance there we should?
Yeah, I'm not sure. I mean, I think it depends on what's going on. If there's something that happens very quickly, right, like you would need a higher frame rate. I think what our model is doing is with these learned prompts, it's learning to pick out important features of all like this huge buffer of frames, hopefully. I mean, like that attention map is maybe one anecdotal demonstration of that it might be doing that. But yeah, I don't know if there's like a standard frame rate. I mean, I think human beings are just different. Like there's even video, like these videos of illusions where they show that like if you show someone an interesting basketball game or something and you like tell them to follow the players, and then humans will miss like a gorilla walking through the court because they're so focused on that one thing. So yeah, I don't know if like that would transfer to a VLM. But yeah.
Actually, just following up on that, that's kind of interesting because it feels like then the frame selection becomes very important. But if you do frame selection for like one task, it's probably maybe not correct then versus frame selection for another task. Like, do you have like, is the frame selection adaptive?
Yeah, no, actually the frame selection, I mean, we sample a fixed number of frames from each segment of the video, which is better than like previous methods, which will just sample a fixed number from the whole video, but that is not adaptive. Yeah.
So you might miss the gorilla, I guess.
If it happened very quickly, we can definitely miss it. Yeah. These models are not like super fine grained. Yeah. But there's also like just the compute requirement, like this is just a trade-off of it's like resolution in images, you know, like how much can you handle? Okay. Thank you.
There's AI social that voting 45.
Yeah.
So, okay. I know.